Hi everyone. This is going to be the first Chem 343 lecture follow-up. Has to do with the lecture on March 23rd. There were only a couple of questions on Piazza regarding it. One question regarded the pinnacle rearrangement. And this pinnacle rearrangement was named after this molecule right here called pinnacle. And when you treated this with sulfuric acid, it would actually do this rearrangement. If you don't use catalytic amount, it just goes a lot faster. We end up with a ketone. So, how the rearrangement works. Is we don't have a good leaving group, but we have a strong acid present that can protonate and make a good leaving group. Now this leaving group is attached to a tertiary carbocation, tertiary carbon, and tertiary carbons form tertiary carbocations quite quickly, like so. Now, normally, tertiary carbocations don't rearrange, because they are at the top of the food chain when it comes to carbocation chemistry. There's only one carbocation that's particularly more stable than a tertiary, and that's a resonance stabilized one. And if we look, here's our alpha carbon, here's a beta carbon, here's a beta carbon, here's a beta carbon. If we move any group from beta 2 or beta 3, which there are just hydrogens of, we end up with a primary carbocation. That's in the wrong direction energy-wise, so that's not likely to happen. But here, if we move one of these two methyl groups, slide it over, we end up getting this carbocation right here. That carbocation, what makes it better than a tertiary is that it's a resonance stabilized tertiary, with this being the major resonance structure. And then another molecule can come and take this proton off. Could be the water that left, could be the conjugate base of sulfuric acid that was generated here. It could even be another molecule of pinnacle. Lots of options to choose from. But there we go. And that's the pinnacle rearrangement. But all it is a carbocation rearrangement. And where to look out for it is when you have two OHs on adjacent carbons, and you have the strong acid present. So the big clue is two OHs on adjacent carbons. The other question had to do with problem 6C. We have this alkene, and it's listed as optically active, and treating it with acid and water. Well, these are the conditions to do an alkene addition, where we have a strong acid to protonate the alkene, and we have a nucleophile to add the resulting carbocation. And the resulting Now, we can protonate on either side, but we're going to protonate to form the more substituted side. This is called Markovnikov addition. So we protonate the less substituted side. That's right here. And you can use either the H2SO4, or since we're in water, you can use H3O+, because when you throw sulfuric acid in water, what you really have is H3O+. And you get the carbocation here. Also, if you take a look, our starting material is optically active. But once we protonate, this molecule now has a plane of symmetry. That means it's achiral. We have lost optical activity, and once you lose optical activity, it's gone. So the product cannot be optically active no matter what now, because we have lost chirality. Now water can add, and it can add from the top side or the back side. We'll worry about that stereochemistry later. And then we just have something take this proton off. It could be the conjugate base of sulfuric acid, or more likely it's just another molecule of water. Could even be the another molecule of alkene. And we have our product. Now, let's take a look at our product. We have a carbocation. The OH could have added from either side. So you can have this. Or this. Both molecules have a plane of symmetry. So they are not racemic, because racemic only applies to chiral molecules. Since these molecules have a plane of symmetry, both molecules are achiral. Now, the relationship between these. Here the OH is trans to the methyl group. On the other molecule on the right, it's cis to the methyl group. We have same connectivity, different interatom distances. These molecules are diastereomers. So both must be drawn. One other question I see on Canvas has to do with problem set 19, 7b mechanism, where this molecule plus 0.5 equivalents of HCl leads to this molecule. Now this is purely a mechanism question where you need to find a way to show the mechanism from A to C, whether or not this is a real reaction. So what I meant by saying half equivalent of HCl, that means that you have lots more of this alkene than you do of this acid. Meaning that chances are you're going to use the alkene more than the acid would. So when you have an acid and an alkene, you can protonate the alkene to form the most stable carbocation you can. And normally, if you have a lot of nucleophiles around, that can add to that carbocation and end up with that as the product. The thing is, we don't have that much of it. Not as much as the alkene. And so, what you can get as, sometimes it's a side product, or sometimes if you use just very little acid at all, you can actually make this the major product and you get what's called a polymer. Is that the alkene can also react as a nucleophile. Way of thinking about it is, instead of this H hydrogen is the electrophile, instead of using this hydrogen as the electrophile, use this entire carbocation. And so you get those 4 carbons from that. And you get the new carbocation right here. And if we were to number these carbons, 1, 2, 3, 4, 1, 2, 3, 4. Here we have carbon 5, 6, 7, 8. 5 is a CH2, now it's attached to carbon 2. That's 5. 6 is this carbon. It's the one with the carbocation because the electrons went away from carbon 6, creating the carbocation at 6. And then you have 7 and 8. And then this, typically carbon-carbon bonds, when you form a carbon bond, it's not really going to be readily reversible at all. But then you have your carbocation, and to get to your product, your chloride comes and adds to it. And there you go.